Hello, welcome to the seventh lecture of Triple E3. We'll just be continuing our discussion on AC circuit analysis, and this time we will transform our AC circuits into complex numbers. So recall that by having a changing voltage and changing current in our circuits, the uh, the inductors and capacitors become uh, another additional element to consider when analyzing our circuits because they react to the change in the parameters in the circuit. That's why they are called reactive elements. Let's simplify our analysis. Instead of using differential equations, we can actually simplify the analysis using what we call phasors. And this is what will be the focus of this lecture. So before we start, let's discuss first complex numbers. Recall that complex numbers consist of a real part and an imaginary part. For example, your number A is represented as a sum of a real number and an imaginary number. So this is actually an extension of your set of real numbers. This is the set of complex numbers. So for complex number A has the real part equal to small a and an imaginary part equal to b. So just some note that the j here represents the square root of negative 1, which represents the imaginary number here. So it's written in j because I is already given to the current. So for electrical engineers, we represent the complex numbers as j. So examples here, the following numbers are complex numbers, A, B, C, and D. Okay? And we call their form a rectangular coordinate form. So with these numbers, we can write them in what we call a complex plane. Okay? So recall when you're trying to plot a real number, you only use a horizontal number line. But if you have an imaginary number, you have an imaginary axis intersecting a real axis. And instead of having a number line, we have a number plane, which this is now your complex plane. So the complex plane is kind of like a Cartesian coordinate system. So where abscissa or the x component is for real numbers and the ordinate or the y coordinate is for imaginary numbers. So for example, our for the given earlier right here, A, B, C, and D, we can plot them on the complex plane. A being 3 plus J4 means 3. So 1, 2, 3 on the x-axis plus J4, 1, 2, 3, 4 on the y-axis. So the others would follow. Okay? So it's easy. So these are your rectangular forms of complex numbers. We move on to what we call the polar coordinate form. In the polar coordinate form, instead of defining the real and imaginary part of a complex number, we are gonna define the complex number using the magnitude, okay, and the angle of the complex number. By magnitude, meaning the length of the distance between the complex number to the origin 0, 0. So to get that magnitude, just think of it as a triangle. Okay, so this is the xy plane anyway. And this would be the x component, this length, and this will be the y component, this length. And the length of this vector here, or this length here, is just defined by our distance formula, square root of x squared plus y squared. And that is this expression right here. For the angle, since this is a right triangle, so the y and the x components are perpendicular from each other, you can express the angle in terms of your x and y components by using the SOHCAHTOA, or specifically the TOA part, which is the tangent. So the tangent of your angle theta is equal to the opposite, which is y, divided by the adjacent, which is x. So that's where this equation came from. Okay? Thus, we can write our complex number a in this form, magnitude of a, angle theta. And this is called the polar coordinate form. Next is we have the trigonometric form. Consider the complex number written in rectangular coordinate form like this and a polar coordinate form like this. Okay. If we're gonna use trigonometric form, um, since this is a triangle defined by this magnitude a, the trigonometric form can be, it's just an offshoot of your rectangular form, but instead we'll write this rectangular form in terms of the magnitude a and the angle theta. So we just combine these two forms together. And knowing that a is this length, which is the x component, this is equal to the magnitude times the cosine of this angle theta. Therefore, we can write a as a cosine theta. B here is just a sine theta. Substitute it in the uh, rectangular coordinate form, we get this expression right here. For example, given that small a is 3, small b is equal to 4, that's 3 plus j4 in your rectangular form, we can express it as something like this. Knowing that we have your a, oh wait, sorry, that's not your 3 plus j4 earlier, it's a different a. Given that a has a magnitude 10, and in angle 36.87 degrees, they can be written in trigonometric form as this expression here. And evaluating the cosine and the sine, you'll be left with this expression here. Okay, so this is your complex numbers. How will it help in analyzing circuits? Well, recall for our time domain expressions for your voltage or current or any voltage or current. Recall that it's a sinusoid with an angle alpha, okay, and a phase shift alpha, okay. F sub m here is the amplitude of the sinusoid. We can define a transformation from your sinusoid to your phasor, as we call it, which is the complex representation of our sinusoids, as this expression right here. Your f of t becomes big F of j omega, which is equal to the RMS value of the sinusoid, angle B, basically the phase shift. Okay? And this is now a complex number, right? So for example, given f1 of t is this, and f2 of t, or sorry, f2 of j omega is this, right? We can write f1 of j omega by getting the 311 divided by square root of 2, which is the RMS value, angle 60 degrees right here. This is the phasor form of the f1 of t source or f1 of t function. This f2 of j omega can be converted back, okay? Given that omega is just omega, well, your f2 of t becomes 10 times square root of 2, which is because since this is an RMS value, so 10 times square root of 2 is this, and 20 degrees is the phase shift, so plus 20 degrees right here. So if we have a sinusoidal source, we can represent it as just a scalar complex number. So instead of expressing it in terms of its time dependence, let's remove that completely and represent it as something else. In this case, a complex number. So this is what we call the Phasor transformation. And as you think of it, how do you use it in analyzing circuits? Well, it's not just the voltage, not just the current. We also have the resistance, the inductance, and the capacitance. Well, we can actually map them into their phasor forms also. Consider the resistor first. So in a resistor, let IR be the current, which is Im cosine omega t. Therefore, there is no phase shift. We can represent this current right here into phasor form, okay? So the magnitude divided by square root of 2, which is RMS, angle 0 degrees, since there is no phase shift in this. Okay. Now from Ohm's law, we can get the voltage across the resistor, okay? Just multiply R, and you get this expression right here. And we can represent this voltage into its phasor form. It's equal to this. By dividing V over I, we can get the resistance of your resistor in phasor form, which is basically just its value times omega, which is the SI unit for resistance. This is basically the phasor model of a resistor. So it doesn't change when we map it to phasor form. If we try to map an inductance, so again, let's do the same procedure. Let there be current passing through the inductance. And knowing that the voltage induced in the inductor is just the derivative of the current, so get the derivative of this, the omega pops out, and your cosine becomes sine, and this sine becomes cosine omega t plus 90 degrees. Okay, this negative sign becomes omega cosine omega plus 90 degrees. By Phasor transformation, this IL becomes this VL becomes this. It's your IL still the same, 0 degrees phase shift. Your VL has a 90-degree phase shift with your RMS value is equal to the amplitude divided by square root of 2. By dividing V and I in lieu of your Ohm's law, we can get some kind of resistance. So quote and quote, some kind of resistance in our inductance. So yeah, you get the point. I can't write that. It's so long and we have no more space. Anyway, so it's kind of a resistance in when we mapped this phasor form or this phasor value from our time domain expression. This inductor kind of becomes a resistor when you map it into its phasor form, with its resistance being complex, J times omega times L. J omega times L. Omega is the frequency of the function, L being the inductance. Okay. For a capacitor, in this case, let the current I be described by this function, still the same function, but the voltage across the capacitor is the integral of the current divided by the capacitance. Therefore, we get an expression for the voltage here. Okay, convert that to phasor form, convert the current to phasor form. Still the same for the current. For the voltage, something like this. Since it's sine omega t, this sine is just basically cosine shifted by negative 90 degrees. Okay, and it becomes this expression right here. We divide V and I. We also get some form of resistance in the capacitor. This resistance is 1 over j omega c. Okay, where did that come from? Well, 1 angle 90 degrees is equal to j, because sine 90 degrees is 1 and cosine 90 is 1. Again, we also have a resistance in the capacitor, quote unquote, resistance. But this time, it's opposite your inductor. Your inductor has positive resistance. 1 over j here is actually negative j over omega c. So your capacitor kind of has a negative resistance, quote and quote. So I'm talking about resistance here, but the formal term for this is actually the impedance. The impedance is an extension of your resistance. If we have real numbers and we can extend them into complex numbers, we can do the same to the resistance of some device. We can extend it to what we call an impedance, where your number has a real part and an imaginary part. So the impedance is kind of like the resistance, but in this case, it's complex, and it's defined by Ohm's law right here. If Ohm's law in the DC case is V is equal to I times the resistance R, Ohm's law in our phasor form is equal to V equals your current times Z. Okay? So, for writing, we represent anything that is complex with an arrowhead. So, representing its complex, or maybe we can use a bar. But for me, I prefer using an arrow. Okay? When I'm gonna type it during exam, a complex number will be bold font with an arrowhead. Okay? So some notes for your impedance for a resistor. The impedance of a resistor is basically its resistance. For an inductor, it's J times omega times L. And for a capacitor, it's 1 over J times omega times C. So we define then XL and XC as the reactances of L and C, where XL is basically equal to omega L, XC is equal to 1 over omega times C. Okay? So the reactances are has a unit of ohms. Okay. Now we have the concept of admittance. It's just the reciprocal of your impedance right here. So for a resistor, the admittance is 1 over R. For an inductor, it's 1 over j omega L, or negative j times BL in 1 over ohms. For a capacitor, it's j omega C, or equal to JBC, where BL and BC are called susceptances. Okay. So to summarize, the equation describing any impedance is algebraic. There's no integrals, there's no derivatives, there's no complication whatsoever. So from your time domain, setting up your differential equation, trying to solve it, it's actually tedious when you think about it. But when we transform them into phasors, we go back to the basics. So we also have an Ohm's law right here, defined by your voltage, your current, and your impedance Z. An extension of your Ohm's law in DC. Which means that all the methods of analysis that we have discussed so far in resistive networks or in DC networks like mesh analysis, nodal analysis, Thevenin's theorem applies to a transformed AC network. Okay, so emphasis on the transformed, since you need to convert it first to a phasor equivalent. Okay. And another note, your phasor transformation is defined through the cosine function right here. So the magnitude is based on the RMS value. So keep note of that when you're transforming your value from your time domain to your phasor domain or vice versa. Okay? So when we are talking about phasor transformation, it's based on the cosine and the RMS value. Okay. So with that in mind, basically, we can reduce the network if we have impedances in parallel. We can basically add them together. If sorry, in series. If it's in parallel, well, it's something like this. So that's just the same as your resistors. 1 over the reciprocal of the equivalent impedance is equal to the sum of the reciprocals of the individual impedances in each branch. Okay. So, yeah. So let's have an example there. Given V of t 100 times cosine 10 t volts. Find I of t and VL of t. First step is to transform everything into phasors. So we transform the source, becomes like this. So your voltage, sorry, your resistor 8 ohms is still the same. And your inductor 0.6 Henry becomes J6 ohms right here. So where did that come from? J omega L. So that's J times 10 times 0.6. Okay, so now the total impedance in this equation, in this circuit here, is just the sum of the impedance of this resistor and this inductor. So that's 8 plus J6. And you can solve for the current by basically getting the voltage here divided by the total impedance here. So that is this expression right here, and it results into this quantity. Okay? So when you divide this, you can just use your calculator, set it in complex mode. Or you can just divide the magnitude of this by the magnitude of this, and you get the difference of the angles, and be you have your result right here. So transform that back into its time domain equivalent. You get the expression for I of t. Okay? So you get your final answer without going through the tedious process of setting up the differential equation of your circuit. Okay? So we have simplified that elegantly using phasors. Now we want to know the voltage across the inductor. Well, you can just use Ohm's law for that. Multiply I of j omega to the impedance of the inductor. So that would be this multiplied by J6. You'll get this and convert it to polar form. Multiply the magnitudes, get this, and the you add the phase angles, you get this. We go back, we transform that into the voltage in time domain. You multiply the magnitude by square root of 2, and the phase is basically just you add it to the cosine function, and you'll have this equation right here for VL of t. Okay? Well, aside from doing that, we can also solve for the voltage across the inductor using voltage division. Okay? So the impedance of the inductor plus the total impedance of the system times the voltage input. Get this expression here times this, the voltage. Okay? And then you just simplify this expression here. You can use your calculator to input that, and you get this expression right here for the voltage, which is the same as what we got earlier. Okay, another example. Let's move on to more complicated circuits. Given that the voltage source has this sinusoidal voltage, find I1, I2, and I3. The currents across each element in the or each branch in the circuit. Okay, so convert first the voltage into phasor. Look at this. Convert the impedances into phasor. Sorry, the reactive elements into phasor form. You get this. Okay. So the transform network is something like this. This is an impedance, this is an impedance, and this is an impedance. Okay. So how do we solve for the uh, currents across each branch? Well, one solution is use network reduction to get the input impedance. What does that mean? You reduce this whole network to get the impedance, the total impedance. That will define I1 of t. So how to reduce the network? First, this branch here is parallel to this branch here. So let me clean that. There you go. This branch here is parallel to this branch. You can get the equivalent impedance. It's equal to 10 ohms. Okay? And the total impedance is just Z1 plus the total impedance of this. So that's this value right here. We can now solve for the current I1 by just doing Ohm's law, voltage across the total impedance divided by the impedance, basically. And you'll get this expression for your current. So this is the current that goes in the system. right here, the current I1 is split into I2 and I3. You can solve I2 and I3 using current division. Okay? So I2 is equal to, okay, the impedance at uh, the, the capacitor, so impedance at this branch here, divided by the total impedance, okay, times the current going in, which is equal to this. This is the current, sorry, this is the impedances, this is the current. So convert that into, what do you call this again? Convert that into polar coordinate form and evaluate the magnitudes, multiply this to this divided by the magnitude, and this, add this to this and subtract this. The final expression for the current is this. Okay. And finally, you can use KCL to get the values of this of the third current I3 of omega, and it's equal to I1 minus I2, which is this. Okay. Convert this into rectangular form, add the real part, add the imaginary part, you get this. Convert it back to your uh, phasor form or your polar coordinate form. And you can now transform that back into the time domain equivalents with like something like this. Okay, so multiply the magnitude by square root of 2 and add the phase to the cosine function. Okay, so that's the solution. That's solution number 1. Solution number 2 is this. Okay, so you can do mesh analysis and assign I1 in this loop and I3 in this loop. Okay, so evaluating mesh 1, that's V of j omega equals Z1 times I1 plus Z2 times I1 minus I3. That's your mesh. Mesh 2 is just ZC times I3 plus Z2 times I3 minus I1. Substitution, you'll get this for your first equation. Simplifying, you get this expression here and this expression here. From equation 2, we can get the value of I3 in terms of I1. Okay, substitute that into equation 1. You can solve for I1. Solve for I1, get this expression right here, which is the same as what we got earlier. You can solve for I3 because I3 is in terms of I1. Get this expression here. And finally, I2 can be solved using KCL. So that's I1 minus I3, which is this expression right here. Transform them back into time domain expressions. You get the same results as what we got earlier. So our what you have learned from lecture 1 to 5, all that hard stuff, you can still use it in our alternating current domain or AC domain. So that concludes this lecture. If you have any questions, do not hesitate to post a comment in our group or in the YouTube comment section below, and I'll happily discuss it with you. Okay. So that is all. I hope you learned something from this lecture. Thank you for listening. I'll talk to you again soon.